Imagine this: the ground beneath your feet starts to rumble. Buildings sway, roads crack, and in a matter of seconds, the world as you know it changes. This isn't a scene from a movie, it's the reality of an earthquake. Every year, the Earth experiences thousands of earthquakes, ranging from barely noticeable tremors to catastrophic quakes that can level cities. But what causes these powerful natural events? In this video, we'll dive deep into the bowels of the Earth to uncover the mysteries of earthquakes. An earthquake is the Earth's dramatic response to its inner movements. The Earth's lithosphere, encompassing the crust and upper mantle, is divided into tectonic plates. These plates, floating atop the semi-fluid asthenosphere, move slowly but ceaselessly. Their interactions at various plate boundaries are the primary catalysts for the seismic activity we know as earthquakes. There are three main types of plate boundaries: convergent, divergent, and transform. At convergent boundaries, plates move towards each other, often leading to subduction where one plate plunges beneath another. This process is responsible for some of the most powerful earthquakes, as well as volcanic activity due to melting subducted plates. Divergent boundaries, where plates move apart, see the formation of new crust as magma rises to fill the gap. Earthquakes here are frequent, but generally less intense. The Mid-Atlantic Ridge is a prime example, a vast undersea mountain range formed by such divergent activity. Transform boundaries present a different scenario. Here, plates slide past each other horizontally, exemplified by the San Andreas Fault in California. The friction at these boundaries can lock plates in place, but as they continue to move, stress accumulates. When this stress overcomes the friction, it releases an earthquake. The sudden release of energy at transformed boundaries often results in particularly destructive earthquakes. The start of an earthquake, or the hypocenter, lies deep underground. From this point, seismic waves radiate outward, causing the ground to shake. Directly above the hypocenter, the epicenter is typically where the most severe effects are felt. The impact of an earthquake varies based on several factors: the depth of the hypocenter, the distance from the epicenter, the type of geological material the waves travel through, and the resilience of local infrastructure. Earthquakes, while appearing sudden and isolated, are part of a continuous geological cycle. They offer insight into the dynamic processes shaping our planet's surface. Each earthquake not only reveals the complex interactions of tectonic plates, but also reminds us of our planet's ever-evolving nature. Measuring the magnitude and intensity of earthquakes is crucial for understanding their potential impact. This process involves sophisticated scales and technologies that help scientists and authorities prepare for and respond to seismic events. The magnitude of an earthquake, indicating the energy released, was traditionally measured by the Richter scale. Developed in the 1930s, this scale quantifies the size of an earthquake based on the amplitude of waves recorded by seismographs. However, for large-scale seismic events, the Richter scale has limitations. Today, the moment magnitude scale, MVO, is more widely used, especially for significant quakes. This scale considers the area of the fault that slipped, the amount of slip, and the rigidity of the rocks involved, offering a more accurate measure of an earthquake's true size. Intensity, on the other hand, is a measure of an earthquake's effects on the Earth's surface, structures, and humans. The modified Mercalli intensity (MMI) scale is used to assess these effects, ranging from I not felt to XII, total destruction. Unlike magnitude, which is calculated from seismic data, intensity is based on observational reports and the impact on people and infrastructure. Seismological equipment such as seismometers are pivotal in measuring earthquakes. These instruments, placed globally, detect seismic waves, allowing scientists to determine key earthquake characteristics like epicenter, depth, and magnitude. Networks like the Global Seismographic Network provide real-time data essential for rapid assessment and response. Accurate earthquake measurements are vital for more than just scientific understanding. They inform emergency response strategies, guide building codes and urban planning, and enhance our comprehension of Earth's geology. Advances in technology, including the integration of GPS and satellite data, have improved our ability to monitor ground movements and stress buildup along fault lines. This progress is crucial for ongoing research in earthquake prediction and preparedness. Each earthquake provides valuable data, contributing to our ever-evolving understanding of these natural phenomena. This knowledge is not only important for the scientific community, but also crucial for the safety and preparedness of societies in seismically active areas. The aftermath of an earthquake can be multifaceted and far-reaching, affecting not just the physical landscape, but also the social, economic, and psychological fabric of the affected areas. Understanding these impacts is crucial for effective disaster management and long-term recovery planning. Physically, the most immediate impact of an earthquake is the damage to infrastructure. Buildings, roads, bridges, and utilities can suffer extensive damage, especially in areas not designed to withstand seismic forces. This destruction poses immediate risks to human safety and disrupts essential services, complicating rescue and relief efforts. For example, the 2015 Nepal earthquake caused widespread destruction of historical buildings and homes, severely impacting the region's cultural heritage and housing stability. Secondary disasters are another critical consequence of earthquakes. These can include tsunamis, as seen in the 2004 Indian Ocean earthquake, landslides, and even volcanic activity. These subsequent events can compound the devastation and pose additional challenges for emergency response and recovery efforts. The economic repercussions of earthquakes are often profound. The cost of rebuilding and repairing damaged infrastructure can burden local and national economies. The disruption of business activities and loss of livelihoods further exacerbate the economic impact. In some cases, such as the 2011 Japan earthquake and tsunami, the global supply chain and international markets can also be affected, demonstrating the far-reaching economic implications of major seismic events. Beyond the physical and economic damage, earthquakes have significant psychological impacts on those affected. The trauma of experiencing such a disaster, along with the loss of homes, loved ones, and normalcy, can lead to long-term mental health issues like PTSD, anxiety, and depression. Community support and mental health services play a crucial role in the recovery process, helping individuals and communities to heal and rebuild. The occurrence of an earthquake often leads to changes in urban planning and building practices. Affected regions typically revise building codes and develop new construction techniques to improve earthquake resilience, aiming to minimize damage and protect lives in future seismic events. The long-term impact of earthquakes, therefore, extends into the realms of engineering, architecture, and urban development. Predicting and preparing for earthquakes are crucial aspects of managing seismic risks, especially in earthquake-prone areas. While predicting the exact time and location of an earthquake remains a challenge, significant advancements in understanding seismic activity have led to better preparedness and response strategies. Earthquake prediction involves forecasting the likelihood of an earthquake occurring in a specific area within a certain time frame. Current prediction methods rely on analyzing historical seismic data, monitoring geological changes, and understanding the mechanics of tectonic plates. Scientists use various tools such as seismographs, GPS systems, and satellite imagery to track changes in the Earth's crust that may indicate potential seismic activity. However, despite these efforts, accurately predicting the exact timing and magnitude of earthquakes is not yet possible. Preparedness, on the other hand, is an area where significant progress has been made. Earthquake preparedness encompasses a range of measures designed to minimize the impact of earthquakes on communities. This includes developing and enforcing stringent building codes that ensure structures can withstand seismic forces. For instance, countries like Japan and Chile have implemented advanced building standards that have proven effective in reducing damage and casualties during earthquakes. Public education and emergency planning are also integral to earthquake preparedness. Governments and organizations conduct regular public awareness campaigns and drills to educate people about how to respond during an earthquake. These efforts include teaching drop, cover, and hold-on drills in schools, developing community response plans, and ensuring that emergency services are well-equipped and trained for disaster response. Technology plays a vital role in preparedness. Early warning systems, which detect the first waves of an earthquake, can provide valuable seconds or even minutes of warning before the more damaging waves arrive. Such systems, operational in countries like Mexico and Japan, alert the public and trigger automated responses such as slowing trains, stopping elevators, and shutting off gas lines. Research into earthquake-resistant design has also led to innovative engineering solutions. Buildings equipped with base isolators, shock absorbers, and other seismic dampening technologies can better withstand the stresses of an earthquake, thereby reducing the risk of collapse and saving lives. Living with the reality of earthquakes is a significant aspect of life in many parts of the world. This continuous adaptation involves not just preparing for seismic events, but also integrating earthquake resilience into daily life, community planning, and emotional well-being. Building resilient communities is at the forefront of living with earthquakes. This involves constructing earthquake-resistant buildings and infrastructure, ensuring that vital services like healthcare and emergency response are robust, and designing public spaces for safety during quakes. Urban centers such as Tokyo and San Francisco have become models of integrating seismic resilience into urban planning, learning from the experiences of past earthquakes. Education and awareness play a critical role. Regular earthquake drills in schools, workplaces, and communities are essential for ensuring that everyone knows how to respond safely during a quake. These practices focus on simple but life-saving actions like the drop, cover, and hold-on technique. Additionally, public awareness campaigns emphasize the importance of emergency preparedness, including maintaining emergency kits and securing items within homes to prevent injury. Community preparedness extends beyond individual action. It involves developing local networks for mutual support in the aftermath of an earthquake, such as community response teams and local disaster management groups. These grassroots efforts are crucial for immediate response and are integral to the long-term recovery process. Psychological resilience is also a key aspect of living with earthquakes. Communities develop coping strategies to manage the stress and trauma associated with seismic events. Mental health support and community solidarity programs are essential in helping individuals and communities recover and rebuild emotionally after a significant quake. Advancements in technology enhance safety in earthquake-prone regions. Earthquake early warning systems, innovative structural engineering, and improved emergency communication networks are examples of technological solutions that contribute to safer living conditions. Smartphone apps providing real-time alerts in buildings equipped with seismic dampening systems are increasingly common, illustrating how technology aids in adapting to earthquake risks. Thank you for joining us on this journey to understand what causes earthquakes. Our planet is a constantly changing and evolving world, and understanding its processes is not just fascinating but crucial for our survival and resilience. Stay informed, stay prepared, and stay curious about our wonderful world.